We meet one more time. So here we go. We are going to do part 4, which is the last part to section 8.5, and it's roots of a complex number. So we're going to do two things. We're just going to derive the formula, and we're going to use the formula. That's essentially it. So let's derive the formula. So the formula comes from, let me write this down. It comes from what we know about finding powers. Excuse me. So I'm going to go ahead and let z equal r cosine theta plus I sine theta, and u equal s cosine beta plus I sine beta. And then we know, well, if I'm going to also say that assume u to the nth is equal to z. So let's go ahead and see what that means. That means if I take u to the nth, now I'm going to go ahead and switch over to cis notation, just easier that way. So u, remember, was s cis beta, but we're raising it to the nth power. And then z is r cis theta. And then we know from working with powers in De Moivre's theorem that the nth power of u can be written as s to the nth cis n beta, and that equals r cis theta. So now we have an equation to work with. If I go ahead and take the absolute value of both sides, if these complex numbers are equivalent, then they should have the same distance from 0. So we can go ahead and take the absolute value of both sides like this. And if we do, remember the distance from 0, that's just r. So I can go ahead and say that the r's, the radii, are equal. So s to the nth will equal r, and that gives us one of our key relationships there. Now, I can't quite do the same thing with the angles. I can't say that n beta is equal to theta. And the reason why we can't just equate the angles is because remember that they're periodic. So, and they come with cosine. They come from doing the cosine and the sine. So, cosine of one angle is going to be equal to the cosine of a coterminal angle. We're adding 2 pi. So basically what that means is that I can't just say that n beta is equal to theta, but what I can say is they'll be equal to each other plus multiples of 2 pi. And the way we're going to do that is just say 2 pi k. And it's kind of implied k is an integer. So that I can do. And that's kind of where our formula comes from then. If I go ahead and take this one right here, the one with the radii, the s to the nth equals r, that means that s is going to be the nth root of r. And over here, if I solve for beta, then I have beta is equal to beta plus 2 pi k over n. And that's, like I said, pretty much where our formula is going to come from. So I'm going to write it down formally, and then we'll take a look. This is nth roots of a complex number. For a positive integer n, the complex number z has exactly n distinct roots given by the nth root of r cis theta plus 2 pi k over n, where k is equal to 0, 1, 2, and so on, all the way up into n minus 1. And there's a formula. Piece of cake, right? It looks more complicated than it is. It really isn't that bad. Let's just talk about a couple of things first before we actually start working with it. One thing is this word distinct. We use that a lot in math. That means different. So a positive integer or a complex number z has exactly n different roots. If we're looking at cube roots, there's going to be 3 different cube roots. If we're looking at fifth roots, there's 5 unique fifth roots for z, and so on and so on. So all of these roots are different. None of them are equal to each other. So that's one thing, the word distinct there. This thing too, right here, this looks more complicated than it really is. And what the heck does all of this mean? So I'm going to go ahead and break it down for you. A lot of books will write it like this, but there is another way to write it, which I think is easier to work with. Basically, I'm just going to separate the fractions. So I'm going to go ahead and just write it as the nth root of r cis theta over n plus 2 pi over n k. What we're going to do is we're going to take our given theta, so whatever the theta is for the trig number that we're working with, we're going to divide that by n. That's going to give us our first principal root. And then we're going to add multiples of 2 pi over n. We basically take one rotation around the circle and divided it into n pieces. So let's say we're taking cube roots. That means n is 3. So we're going to start with theta over 3. And then we're going to add multiples of 2 pi over 3 to that. We're going to take 1/3 of a circle and add it each time. So let's go ahead and take a look at this idea also of roots. Roots, why is there multiple roots? Let's just take a look at this example. I could ask for the square root of 25. That's one problem. Or I could ask for the square roots of 25. Wait, what's the difference between these two problems? I mean, obviously this one has an s, square roots, implying there's more than one. But other than that, really, aren't they the same? This is the square root of 25. This is the square root of 25. So what's the difference? The difference is how it's written. When it's written like this, the square root of 25, with a radical symbol, this implies the principal root. So that means that the answer is 5, because 5 is defined as the principal root of square root of 25. What's the principal root? Wait for that. I'll go ahead and get to that a little bit more. But the square roots of 25, this would be 5 or -5. That's because I can take 5 and square it and get 25, or I could take -5 and square it and get 25. Either way, it's the same thing. So that's why these are both square roots, but the square root of 25 is just 5. The principal root is going to be the first angle. Going up to this formula right here, it's going to be when you're dealing with theta over n. When you got theta over n, and you don't add anything to it yet, that's your principal root. So you can kind of think of it as like the first angle. And when you use this formula to find the square roots of 25, 5 is going to end up being your principal root. Just know, like for positive numbers, the principal root's always positive. But that's how it works. So we do have multiple roots here. And so that's how that's why this formula then talks about roots. There is more than one root. Okay, let's take a look at an example of using the formula. I'm going to go ahead and go to a new page. All right, what if we want the square roots of 16 cosine 60 degrees plus I sine 60 degrees? So what I like to do is I do a little bit of work ahead of time, and then I do my answer. So I'm going to go back actually really quickly to this form of the formula right here. So I find what the nth root of r is, and that's just going to be, sometimes it's straightforward. Sometimes it takes a little bit of work though, so it kind of depends. So we have that. And then I like to find these two pieces here. I like to find theta over n, so where am I starting? And then I find 2 pi over n, what am I going to add each time? And then I can write my answers down really easily. This first example, because it's just dealing with square roots, isn't going to be very exciting, but when we do other examples, it'll make more sense. So back over here to this guy. I know that for r, I'm going to use the square root of 16, which is just 4. So like I said, sometimes it's really easy. And then for theta, we're going to start, so theta starts at 60 degrees over n. And in this case, n is 2, because I'm talking square roots. So that's 30 degrees. And then I'm going to add 2 pi, or in this case 360 degrees over 2, which is 180 degrees each time. So then my answers, I know it's square roots, 2, so I'm going to have 2 different answers. So I'm going to have, each time my r is 4, and then, excuse me, I just go ahead and start at 30 degrees because that's where theta starts at, and then I add 180 degrees each time. In this case, I only have to add it one time. So I add it once, and I get 210 degrees, and those are my answers. If you have to change it back to standard form, you change it back to standard form, but that's it. So the formula makes it look more complicated than it really is. Let's go ahead and do another example, one that's a little more involved. Let's find the 5th roots of 32 cosine 5 pi over 6 plus I sine 5 pi over 6. So let's go ahead and do that. And I'm actually going to do these, I'm going to, for your homework, you're going to have several parts. So I'm going to go ahead and do this problem as if it was your homework. So the first thing we need to do is actually find the 5th roots. So this is where, like I said, I kind of do this grunt work before. I find r, which is going to be the 5th root of 32, which is just 2. And then I get my information about theta. Whoops. So theta is going to start, theta starts at the given theta, which is 5 pi over 6, divided by 5, because I'm dealing with 5th roots. So that's going to be pi over 6. So I'm going to start at pi over 6. And then I'm going to add 2 pi over n, and again, n is 5 each time. All right, so let's go ahead and do this. I know I'm going to have 5 answers because I'm dealing with 5th roots, so I always just set up my answers. I'm going to have 5 of these guys. And then cis. And now it's just all about the angles. So I'm going to start at pi over 6, and then I'm going to add 2 pi over 5 each time. Now I should go ahead and get common denominators here, make my life a little easier. So I need to use 30 for a common denominator. I'm going to change this pi over 6 to 5 pi over 30. And then I'm going to add 2 pi over 5. And remember, 2 pi over 5, whoops, is 12 pi over 30. So I'm going to add 12 pi over 30 each time. Let's put this in a little cloud. So add 12 pi over 30, so I get 17 pi over 30. Add 12 pi over 30 again, and I'm going to get 29 pi over 30. And I just keep doing that. Add 12 pi again, 12 plus 29, 30, 41 pi over 30, and do it one more time. 12 plus that is 53 pi over 30. If I really wanted to check, I can go one more, add 12. So I add 12 and I get 65 pi over 30. First of all, notice this is bigger than 2 pi. So I've gone too far around the circle. I'm starting to go around again. I'm starting to repeat myself. If I subtract 2 pi from that, I get 5 pi over 30, which that's where I started. So I know I'm on the right track. All right, so I'm going to go ahead and get rid of that, though. That was just for checking. I don't really need that in my answer. So there's my answers. I'm just going to simplify any of them that I can, and it looks like the only one is that first answer. So it's 2 cis pi over 6, and then the rest of them, I'm just going to copy over. And there's my answers. Da, da, da. It's really that easy. All right, so like I said, your homework's going to ask you to do a little bit more. So one thing is, like after you find all the roots, they want you to graph the roots. So let's go ahead and represent these graphically. I'm going to go ahead and get rid of this thing. All right, so my radius for all of these is 2. All of these fall on the same circle with a radius of 2. So I'm going to go ahead and set up my complex plane. And then I'm going to just do my best to make a circle here with a radius of 2. All right, so we got that. Oh, that's a pretty good circle. Go me. Okay, so let's see. We need to go ahead and figure out where all these are. So let's go ahead. Pi over 6 we know is 30 degrees. And let's go ahead and estimate 30 degrees right there. But now let's see, 17 pi over 30, that's a little bit bigger than pi over 2. Pi over 2 would be 15 pi over 30. And so this is a smidge bigger. So I'm going to put that right there. I'm going to do my best to estimate these. 29 pi over 30, that's just under pi. And so I'm going to put it right there. Okay, so 30 goes into 41 once with 11 left over. 11 over 30 is a little less than 1/2. So this is a little less than 3/2 pi, 3 pi over 2. So I'll put it right there. And then 53 pi over 30. If I take out 30, that's 23 over 30. 23 over 30. It's a little more than 3/4 of the way over. And estimate it like right there. Take a look around the circle. Do you notice how these are evenly spaced around the circle? It's always going to happen. And you should notice that. So that's another nice thing about these is figure out where you're starting. So you take the original angle and divide it by 5. That's your starting point. And then each time you're going 1/5 of the distance around the circle, and that's what gives you your 5 roots. That's why each time we add 1 rotation divided by 5 to find the next angle. So they want you to notice that. And then the other thing that they want you to do is just change your answers back to standard form. But remember, you can just go ahead and work them out. Changing it out to standard form, have a calculator handy. If you don't have a graphing calculator at home, use Desmos. Use an online calculator. If anybody has an Android phone, you want a graphing calculator for your phone that looks just like the 83s or the 84s, let me know. I can hook you up. But yeah, so there you go. There it is in a nutshell. All right, enjoy.